This time we're going to discuss about catabolism of lipids, particularly of fatty acids, and the name of that particular pathway is beta oxidation. And to explain why it's named as such, we will go to that later. But let's start first by focusing on the initiation part of beta oxidation. The actual oxidation is here, but there's a step, or there are certain things going on before that happens. So the reason is that the first reaction here, step number 1, requires a fatty acid combined with coenzyme A. So if you have a free fatty acid outside, it cannot really be accommodated unless it goes through certain steps. Alright? So in general, the actual cycle has 4 steps, but before that, there's a series of reactions going on. First, you need to combine the fatty acid here, this is the fatty acid, RCOOH, with coenzyme A in order to form the combination of coenzyme A and the fatty acid. You could call this the fatty acyl coenzyme A. This is the form that will be accommodated by the mitochondrion's intermembrane space because the free fatty acids lie around the cytosol. Alright, in order for them to get inside the intermembrane space, they need to be complexed with the coenzyme A. So after that has occurred, we have here fatty acyl coenzyme A, and it will now be accommodated by another molecule, and that is carnitine. So what happens is that the coenzyme A is liberated, so it becomes removed. So now the ones that combine are the fatty acid, alright, and the carnitine. And this is essential because carnitine would be the assistant of the fatty acid in going from the intermembrane space down to the matrix. And it will be like that. But I said that beta oxidation requires a starting material of fatty acid complex with coenzyme A, and this is not coenzyme A. So what happens is that it will liberate carnitine. It will actually return it to the intermembrane space, and there are free floating coenzyme A's somewhere in the matrix. Alright, those are the ones that would combine with this fatty acid in order to come up with, finally, tada, the fatty acyl coenzyme A inside the matrix, as opposed to this one, which is outside the matrix. And so now we start with the actual beta oxidation. Before that, by the way, all of this are pre-beta oxidation steps, and certain enzymes are participative here. So here, the enzyme that allows the formation of fatty acyl CoA is, well, very obvious, fatty acyl CoA synthetase. Then for carnitine to complex with the fatty acid, we use enzymes known as carnitine acyl transferases. Alright. When you're going to talk about energetics here, the entire series of steps that happened here they did not produce, they consumed 2 ATP. So you assume that for every beta oxidation, before it happens, you invest 2 ATP, just like the initial phase of glycolysis. And now we go to the actual oxidation part, or the cycle, which consists of 4 steps. I'm going to fold this. So this is the actual cycle part. So you start with the fatty acyl coenzyme A. I put labels on it, 1, 2, 3, wherein carbon number 2 is the alpha and carbon number 3 is the beta. We will see if it has use later on. What happens is that from step 1, there's a formation of a double bond at the expense of 2 hydrogens, right? So the step here is actually dehydrogenation. And the name of the enzyme that does that is simply acyl coenzyme A dehydrogenase. Very simple. You have a fatty acyl-CoA, then you dehydrogenate it. So the name of the enzyme is very, very indicative of what's going on. So now, when you do that, you now result with an alkene, but it's also an acid derivative bonded to coenzyme A. So this is termed as an enoyl coenzyme A. So now in step number 2, you remove the double bond and you added water. Remember, HOH is H2O, which is water. So the process or the reaction is hydration. And the enzyme responsible is, again, the name of the substrate was implied, enoyl-CoA. This time, we call this one a hydratase. Alright, there is an addition of water. Steps 1 and 2 are important because out of the 4 steps, these are the 2 energy generating portions. In step number 1, there is a production of the reduced form of FAD. And in step number 2, there is production in the reduced form of NAD. And those are the only energy generating phases. So 2 out of 4 steps are energy generating. Okay, now in step number well, we're not yet done. We have 2 more steps, so let's finish it. In step number 3, we have this substrate. Alright, this is carbon number 1, this is carbon number 2, carbon number 3. The 3 here is also beta, so this could be called as a 3-hydroxy acyl CoA, or you could also name this as a beta hydroxy acyl CoA. And what happens from this one to this in step number 3 is that the OH transforms into O. So there's oxidation, simply oxidation. And the enzyme responsible for this one is beta hydroxy acyl CoA dehydrogenase. So you used to have beta hydroxy, now the hydroxy became a keto group. So now the name of the resulting compound is a beta, not anymore hydroxy, but a beta keto acyl CoA. Alright, and this is where it got its name from, beta oxidation. Right, we have a beta hydroxy group here. We oxidize the beta hydroxyl. That's why beta oxidation. Very cute, right? So the step number 3 is responsible for the name of the cycle. Anyway, we're not yet done. We're at step number 4. What happens is that this is not obvious at first, but I want you to look at the numbers. We started off with carbon number 1, 2, 3, right? But here we ended up with 3, 4, 5. And what's missing is 1 and 2. Where did 1 and 2 go? Actually, what happened is that 1 and 2, along with the original coenzyme A, were released as, what is this? 2 carbons with a coenzyme A. 2 carbons with a coenzyme A. Yes, my friends, this one is acetyl-CoA. Meaning that in every cycle, every round of beta oxidation, you chop off 2 carbons, which would then become acetyl coenzyme A. Alright? And you are left now with carbon number 3 at the forefront. And now this coenzyme A is actually part of a new, or is actually a new coenzyme A, because the original coenzyme A was taken along with the 2 carbons that were cut off. So in addition to the production of FADH and NADH, you also have acetyl coenzyme A as an energy generating process. Because why? What happens to acetyl coenzyme A? It will undergo TCA, and we know that in the TCA cycle, a lot of cofactors are being produced. So that means a lot of energy can be generated from just one round of beta oxidation. Also, I would like to note that there is a certain formula for us to remember. That is, for us to remember the number of acetyl coenzyme A's, we simply count the number of cycles plus 1, or inversely, the number of cycles is equal to the number of acetyl-CoA minus 1. And how do we know the number of cycles? The number of carbons in the fatty acid divided by 2. So for example, I have an 18 carbon fatty acid. How many cycles would it give us? Alright? I mean, sorry, not the number of cycles here, but the number of acetyl coenzyme A. What's important for us to know that in every cycle we reduce 2 carbons. So for example, in an 18 carbon compound or fatty acid, we are supposed to produce 9 acetyl CoA, right? Because for every cycle you chop off 2. But how many cycles would that take? Number of cycles is equal to acetyl CoA minus 1. So if we have 9, 9 minus 1 means 8 cycles. In order for us to visualize that better, I'm going to get a sheet of paper. Alright. Let's visualize, for example, just a 10 carbon compound. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright. So if we have 10 carbons right here, we would assume that we would have 5 acetyl coenzyme A's and then 4 cycles, because the number of cycles again is acetyl CoA minus 1. How did that become like that? So let's visualize. For every cycle, we cut off 2 carbons, right? So this is the first 2 carbons that will be cut. 1, 2. Then another 1, 2. Then another 1, 2. Then another 1, 2. How many cycles did I go? Did we go through? 1, 2, 3, 4. 4 cycles only. Alright? And then we ended up with how many? 1, 2, 3, 4, 5. 5 acetyl coenzyme A's. But this is considering that we are completely oxidizing the entire fatty acid. What if, for example, with the same fatty acid, I only reduce it so that it would result to 1, 2, 3, 4 formation of butyric acid. So if we have 10 carbons and then we have 4 carbons, how many was lost? 6 carbons was chopped off. And it would translate to 3 acetyl coenzyme A's. But how many cycles would that take? Let's see. So we need 3 acetyl coenzyme A's, right? So we have 2. We have 1, 2, 3, 4, 5, 6, 7, 8. This is only 10 carbons pala. 8 carbons. So there, you have 10. Sorry. So how many cycles would it take us to reach the acetyl coenzyme A's? 1, 2, another 2, then another 2. So in order for us to get 3 acetyl CoAs, we needed 3 cycles. And how is that so? Alright, why are they the same? Not the cycle being 1 carbon lower. This is because it is only in the last step wherein you have 4 carbons here, right here, that in 1 cycle you would get 2. Because at the last step when you have 4, 1, 2, 3, 4, in just 1 cycle you get 2. But if you do not reach that part, you would assume that the number of acetyl CoA would be the number of cycles. Alright? So meaning that the formulae I have mentioned, which are these, are only applicable when you oxidize it completely, but not applicable when you limit your oxidation to a particular carboxylic acid. Not complete oxidation. So this is just partial. Alright. So we will be able to interpret that more clearly probably when we have examples regarding calculation of ATP. But I hope that you kind of understood what I mean in this particular portion when we count the number of acetyl coenzyme A's and the number of cycles.